When Thomas Alva Edison invented the light bulb, it's a sure bet that very few people, if anybody, foresaw its consequences. The lighting up of the planet like a star. This is one of the most beautiful and thrilling images of our presence on Earth. This blazing glow, a man-made phenomenon that establishes the borders of the first world. It's also evidence of the energy we waste, of the light we let dissipate into space. From the advent of fire to man's control of the atomic building blocks of life, humans have diligently attempted to control nature, control progress, control the energy ensconced in the earth. This car practically emits no adverse contaminants. It's the Nacar 5, one of several prototypes developed by Daimler Chrysler. Its engine runs on methanol, a chemical compound that acts like a kind of storage device for liquid hydrogen. This car can reach a speed of over 150 kilometers per hour and cover a distance of 450 kilometers without refueling. Methanized hydrogen, in combination with oxygen, produces energy. This is the most advanced automobile in the world to date, using fuel cells. Hydrogen, of course, is plentiful, it's efficient, and it's clean. It's one of the universe's most basic elements, and just possibly may become one of our most important sources of energy in the future. Half a million years ago, the first hominids figured out how to unleash the chemical energy contained in wood into light and warmth. They discovered fire, and thus began mankind's search for ever more sophisticated sources of energy. Fire provided light, and it heated caves. It cooked food. With fire, we were able to work with metal, make glass, and bricks to build houses. Classical Greek mythology adopted fire as the symbol for mankind. The ancients said Prometheus stole fire from the gods and gave it to men to turn them into supreme beings. Man has evolved side by side with the energy he has harnessed, needing it and controlling it. There was a time when we relied only on animals, rivers, and the wind. Around 50 BC, the Romans discovered hydraulic power and used it to grind wheat and pump water. Coal-fired power arrived in the Middle Ages. Actually, the term energy didn't enter the common lexicon until the end of the 18th century, when James Watt invented the steam engine and gave rise to the Industrial Revolution. The Industrial Revolution was a qualitative advance in human history and with respect to mankind's relationship to nature. Coal was the main source of energy for decades. Only in the mid-19th century did certain technological inventions demand the availability of new types of fuel. The first oil well was drilled in 1859 in Pennsylvania, in the United States. This dark, viscous liquid, formed in the Earth's womb over hundreds of millions of years, fired the first combustion engines. And factories, automobiles, trains, and airplanes. That was when the world seemed to start going faster. A century and a half later, the automobile has taken its place as one of the most representative icons of the state of human existence and progress. It's also the most emblematic feature of our species' tendency to waste resources and contaminate our environment. There are more than 6.3 billion human beings in the world right now. On average, each one of them uses about 1.6 tons of oil per year for energy. However, we should clarify this statistic because, in fact, certain nuances should be pointed out. For example, in the United States and Canada, per capita oil consumption is around 8 tons, while in dozens of less developed countries, the figure doesn't even reach 500 kilos, 16 times less. This doesn't necessarily imply that the inhabitants of the world's poorer regions are better energy conservationists, but rather that the statistics don't take into account the fact that over a third of the people living on this planet don't have access to electricity. As with food distribution, cycles of energy production and consumption clearly point to the marked differences between rich and poor countries. The developing countries, with 80% of the world's population, use less than 1/3 of all the energy produced in the world. Nevertheless, they suffer the same negative consequences of the planet's overall profligacy. The most serious consequence of all may be global warming.
We believe, seriously, that climate change is a major threat for mankind. And so we think that Kyoto is only a very first modest step in order to try to introduce the new policy, but we must do much more than that. Kyoto for Europe means 8% of reduction in 2010, between 2008 and 2012. But we need not decrease 8% our emissions. We need to decrease 60 or 70%. And this means radical new technology. We are seeing this technology emerging. This technology is mainly on the transportation sector, that is the sector that is growing faster in terms of energy demand. We are seeing the fuel cell development. And all the major car manufacturers are promising between 2003, 2004, 2005 of bringing the first pre-commercial fuel cell car. And so I believe that in 10, 15 years, we will see fuel cell erupt as a major technology that will enlarge the portfolio of fuels to produce hydrogen, because fuel cells run with hydrogen to produce only water. This will be in the first phase a push also for natural gas. That's why natural gas is now the preferred fuel for power generation and will be also for motor propulsion. And on the second step, we will see, I think, renewables making a visible entrance in 10, 20 years' time with extremely competitive wind power that's now being almost competitive, and probably with breakthrough technology in PV, in photovoltaics. So I believe, like Shell, that by 2050 we will have 50% of our needs supplied by renewables.
Beneath this glacier in the French Alps is a medieval road that in its time was much traveled. This shows us that the Earth's climate changes, and not only over thousands and thousands of years. In a way, even using the term climate change seems somewhat redundant, since a main characteristic of climate per se is its variability. Micro air bubbles deep in the ice of the Arctic and the Antarctic may hold the key to understanding the Earth's climate and the changes it is undergoing. Researchers have determined the temperature and characteristics of ancient pockets by analyzing these bubbles buried under several kilometers of age-old ice. Coral and the growth rings of fossilized trees yield accurate temperature records. For instance, we know that 250 million years ago, the Earth's average temperature was at least 5 degrees higher than it is today. The change, though, from then until now, took place gradually, and animal and plant species had time to adapt, to change, as it were, with the changes. In the past few years, however, we've seen that the climate is changing so fast and on such a large scale that the consequences for life and the world's economy could be nothing short of catastrophic in the short term. Decades from a human perspective, the blink of an eye, geologically speaking. The Earth is warming up slowly but surely, and its average temperature has increased almost 1 degree since the mid-19th century. Experts from around the world, meeting at an intergovernmental conference on global climate change, developed forecasting models that suggest that in the 21st century the warming trend will actually accelerate and that temperatures may increase between 2 and 5 degrees. There are very few scientists now who deny that the Earth's climate is changing. Global warming is basically caused by two factors: natural alterations involving solar forces and human activity.
Over 50% of all climate change has been recorded in the last 150 years. At least half of the overall effect of those changes in the first 100 years was due to natural changes in the energy received from the sun. Over the past 40 or 50 years, however, nearly 70% of global warming can be traced to the increase of greenhouse gases, while the rest, 30 to 40%, is due to natural alterations in solar energy and solar wind. Therefore, the problem is that there are many causes for radiation imbalance. Radiation balance is the key factor in climate stability, so anything that affects radiation balance affects the climate. We cannot say that climate change is caused only by fluctuations in solar winds or by changing amounts of solar radiation. Neither can we say it is caused only by the emission of greenhouse gases. All of these factors have an effect at the same time. However, if one day we do attribute future climate changes to greenhouse gas emissions, it will be because that factor will have prevailed most forcefully on the balance of atmospheric radiation. Therefore, we must say that we are necessarily concerned by increasing amounts of greenhouse gases in the atmosphere, and that they certainly have the potential to cause serious climatic changes in the 21st century.
Our energy production model has a terrible impact on the environment, particularly because it unleashes tons of greenhouse gases into the atmosphere. These noxious gases were identified in the Kyoto Protocol as the major causes of global warming. The largest share of these contaminants come from industry and transportation, from our reliance on fossil fuels. Fossil fuels, most notably coal and oil, are responsible for the increase of carbon dioxide in the atmosphere. Fossil fuels are thought to be responsible for 2/3 of the greenhouse effect, a development which threatens our planet with serious climatic changes. Currently, the atmosphere contains around 360 parts per million of carbon dioxide, while in the 18th century, there were only 280 parts per million. This increase has been caused by human industrial activity, which has spewed into the air a large part of the CO2 contained in coal, oil, and gas. One of the problems associated with climate change is the effects it might have on the levels of the seas and oceans. Around the world, the sea level is rising at approximately 2 millimeters a year. It's known that increased sea temperature causes the volume of seawater to expand, but this really only explains 0.4 millimeters. Melting the water from continental glaciers contributes another 0.35 millimeters to the equation. But that still leaves a millimeter or so to account for. Some hypotheses attribute it to melting water from the glaciers in Greenland and Antarctica. Other hypotheses simply can't explain what's happening. But this much seems certain. It's one of the most pressing challenges facing humanity, given the fact that 75% of the world's population lives near coastal areas. If the ice in the Antarctic melted, we would be witnesses to a disaster of practically unimaginable consequences. Seas and oceans would rise by some 65 meters. In New York, for example, that would mean we would only see the very top of 40-story high skyscrapers. And even if this worst-case scenario does not occur, a rise of just 1 meter would have devastating effects around the world, especially for those who depend heavily on agriculture. Entire countries, such as Holland or Bangladesh, would be wiped off the map. Renewable energy sources are clean and plentiful. They won't ever be depleted for as long as the Earth exists. Their source is solar radiation, a fabulous font that could provide us with over 20 times the energy contained in all the fossil fuel reserves on the planet. Wind, water, the sun, biomass, the Earth's inner heat. These are all renewable energy sources, the keys to keeping the world running in a not-so-far-off future.
Renewable energy sources are exploding in terms of deployment, and we are seeing their growth between 30–40% some years, mainly wind power and photovoltaics. We think that biomass has a large potential, but the logistics are quite complex in order to have the same type of taking off. Anyway, we know, because we have been following the learning curves of these technologies, that we are approaching very, very fast the competitive edge with conventional ways of producing power. So we consider that in the next 10 years we will see a big development of renewables.
The future of renewable energy sources is very promising, but it's not an easy challenge. Besides overcoming the scientific and technical difficulties involved, it will be necessary to prepare the world for the qualitative changes that society in general, and the planet's economic structure, would undoubtedly have to adopt. Critics talk about the increased costs of production, though arguments to that effect may not be as strong as they might seem.
The generation of a kilowatt hour, if we were able to compute all the costs inherent in generating a kilowatt hour from heat, coal, or gas, we'd realize that there are certain expenses we don't take into account when estimating the actual cost of an electricity company or a power distributor, because costs are computed as part of a state's overall operating expenses. For instance, the social costs of mining or government subsidies. There are fuel transportation costs, safety plans, etc., etc. These aren't included in the cost of a kilowatt hour. Therefore, we cannot compare the cost of producing a kilowatt hour with wind turbines, say, with kilowatt hour produced from thermal power, because the wind kilowatt hour doesn't include the environmental costs, while the other sources do. If we took this into account, a kilowatt hour produced from wind would be much cheaper than all other sources. This means that what's happening today is we have to somehow compensate the production of a wind kilowatt hour so we can actually buy it at a coherent price.
Wind power is mankind's most ancient source of energy. The first sailboats were invented around 5000 BC and relied on the wind to transport people and goods over remarkably long distances. The first windmills were built in Asia 2,000 years ago and were adopted in Europe in the Middle Ages. Nowadays, we have these rather fascinating devices, aerogenerators. These modern windmills are extremely sensitive mechanisms and only start operating when wind velocity reaches 4 or 5 meters per second. The movements of the rotors feeds a generator, and the resulting energy goes directly to end users. Their total share of power production is still relatively low. Even the most productive aeolic generators don't have a capacity of more than 1,000 kilowatt hours. However, modern prototypes reportedly produce up to 3,000.
I think we are still pretty green, pretty immature, and we have a long, long way to go. Technically, we can easily go much, much further. Energy from windmills could easily supply 20 or 30% of our needs. There are no technical problems inhibiting us from reaching that level.
Wind power currently generates 2% of the world's electricity, but it's expected to increase its share to 3% by the year 2006. At this stage of the game, it's the most advanced of all the renewable energy sources, but it's not the only one. They usually grow by the roadside, and when we see them, we do our best to avoid them. Nobody wants to get pricked, right? Of course, farmers hate them because they ruin crops. Yet lo and behold, they hold the key to one of the safest alternative energy sources we might exploit in the years to come. It's the common thistle, and it just might be a fine source of fuel in the near future. Obtaining energy from biomass entails the use of each and every renewable organic resource. Its surprising possibilities take us back to the origins of mankind. Wood was one of man's first fuels. Of course, we still burn wood, but the range of organic fuel sources is so much wider now. Today, there are power plants operating on straw and almond shells. The generation of energy from organic material has as a byproduct CO2. But this would be absorbed by the very plants that would then be used to produce more energy. The net result would actually be a win-win situation. Biomass, like all the other renewable energy sources, is very environmentally friendly. % of our current energy consumption comes from biomass. But once again, we have to explain our numbers. Most of that energy, as much as 90%, is generated and consumed by developing countries. Biomass sources satisfy the energy requirements of some 2 billion of the poorest people in the world. Meanwhile, the developed world is hard at work developing new technologies to take full advantage of these plentiful sources of clean energy. Our planet receives from the sun 4,000 times more energy than we consume. This is expected to continue for the next 5 billion years or so. From our humble perspective, it might seem like solar energy was practically infinite. The outer layer of our atmosphere receives on average 340 watts of light and heat per square meter. Clouds or ice or snow masses reflect about 30% of that. But even so, the sun sends us over 120 billion megawatts of energy. In order to produce that much energy, we would need 21 million nuclear power plants. Solar energy heats the earth and the water in the oceans. Plants use it for photosynthesis. Mankind is doing its best to develop ways to harness solar power to meet our daily energy needs. These panels are designed to capture heat from the sun in the form of infrared radiation. They are located in Almería, in southern Spain, at the largest European solar energy research center. The result is perfectly practical for everyday needs. Solar energy heats water and powers heating systems. And best of all, it's very inexpensive. If we had fields of solar energy collectors like this one, we could collect enough heat to generate electric power or operate factories and anti-pollution devices. But the future of solar energy depends on photovoltaic cells, which are semiconductors that transform light into electricity. They work all right in wristwatches or calculators, but they're still too expensive and rudimentary for tasks of greater dimension. At this stage, they can only use 18% of the total amount of energy they receive. The most optimistic scenarios predict that solar energy will reach a level of significant production in about 2015. By then, more powerful storage cells will be cheaper and much more efficient. Those cells might one day be placed in outer space to collect solar energy directly from the sun.
The development of renewable energy sources is conditioning certain technological considerations and political, administrative, and social considerations as well. From a technological point of view, their evolution is unique. Over the past 20 years, wind power has evolved a great deal, and technically speaking, it has become very reliable, inexpensive, and a profitable source of energy. Photovoltaic energy, on the other hand, is taking longer to become profitable. Instead of 20 years, it may take 30 or 40 years. But we are definitely on the right path. At any rate, certain political positions are holding back its progress, and only political decisions can provide the necessary boost that the field of renewable energy requires to become viable.
This futuristic scene could become reality relatively soon. Sophisticated devices orbiting the Earth. Machines designed to collect solar light, turn it into microwaves, and relay that energy to a system of Earth-based antennas. To collect the same amount of energy produced by a 1 billion kilowatt nuclear power plant, however, we would need to assemble a 1 kilometer square network of solar panels. It would only weigh about 800 tons. All the light and heat from the sun have their origin in hydrogen, a natural fuel that is the most abundant element in the universe. Hydrogen is the fuel of life. Scientists and technical experts are studying hydrogen very closely. Some believe there may come a day when nobody has to worry about energy. "75% of the universe is made up of hydrogen. On the Earth, however, the percentage is much lower. A large share of all the atomic hydrogen and molecular hydrogen that probably existed here once upon a time drifted off into outer space. The rest makes up an important percentage of our planet's water and organic substances. Hydrogen's potential as an energy source resides in its capacity to bond with oxygen to form water. Though it may seem strange, this is not so different from the process of burning fossil fuels or biomass. The energy potential, however, is much greater. The same amount of hydrogen could generate 3 times more energy than natural gas or gasoline, for example, and 5 times more than coal. We know of no fuel, in fact, that is more efficient than hydrogen. Also, you don't have to burn it to use it. These are fuel cells. They're designed to generate electricity at normal environmental temperatures. They work by bonding hydrogen to oxygen by means of a catalytic membrane. In Japan, the US, or Europe, the first commercial fuel cell-equipped vehicles are already running. They're similar to gasoline-powered vehicles and offer many intriguing advantages. They don't pollute, they don't make noise, and they run on an endless source of energy. The only drawback is that current hydrogen technology is still very primitive. Almost all the hydrogen that exists on Earth is in water or organic compounds, and splitting the hydrogen atom is still very expensive. Right now, hydrogen as a source of energy is limited to certain special applications such as space exploration. In order to harness the potential of hydrogen on a practical level, scientists will have to first answer a few difficult questions. For example, liquid hydrogen is extremely flammable and therefore dangerous to handle. Also, fuel cell catalysts are made of platinum, which is a very rare and very expensive metal. The total amount of platinum in the world could not even replace a fraction of the cars currently running on our roads. Nevertheless, forecasts are fairly optimistic. Some experts believe that hydrogen will soon be used much like the way we use gasoline today. They say that in a few years, we might very well be able to produce viable energy from water. We might produce it at solar energy power plants, and the big automakers may find an alternative for platinum. On July 16, 1945, the first atomic bomb was detonated in Trinity, New Mexico. 1 gram of plutonium was enough to generate 12.5 kilotons of destructive power, the equivalent of 12,500 tons of dynamite. As has happened so often in history, military science was one giant step ahead of civil society. The atomic bombs dropped in the Second World War were based on nuclear fission. A neutron bombards a heavy nucleus, such as the nucleus of uranium or plutonium, and the nucleus splits into 2 lighter nuclei. The collision releases new neutrons that bombard the new nuclei. This becomes a chain reaction and releases tremendous amounts of energy. This process of nuclear fission is the same one that today produces 17% of all the energy consumed on Earth. If we had to resort to burning fossil fuel for this same amount of energy, we would unleash 700 million more tons of carbon dioxide into the atmosphere than we already do on a yearly basis, roughly the same amount spewed out by the 200 million or so vehicles in the European Union countries. The general public, however, still thinks of nuclear energy as more dangerous than advantageous. The terrible accidents that have occurred at 3 Mile Island and Chernobyl are not easy to forget, even if modern nuclear power plants are much safer. Of course, the future of nuclear energy does not depend just on safety. Like any other industrial activity, the generation of energy from nuclear fission produces contaminating residues as well. In this particular case, the waste products are extremely dangerous, and we still don't know how to best handle them. Nuclear fission produces byproducts that contain varying percentages of radioactivity. Some of those materials will continue to be radioactive for several hundred, thousand, or even hundreds of thousands of years. Some countries, such as the United States, Finland, and Sweden, are still studying ways to safely store these residues in underground sites, but completely acceptable solutions have proved to be quite elusive indeed. Nuclear energy does not contribute to the alarming changes in the Earth's climate, but neither is it as clean as it might seem. We've built much safer nuclear reactors and developed increasingly sophisticated materials and installations, but we still don't know what to do with our nuclear waste. Maybe someday in the future we'll have no choice but to build nuclear waste dumps far away from planet Earth. However, right now, that's still the stuff of science fiction.
The hottest thing that's happening now has to do with fuel cycles. As I said, we're looking for greater efficiency. It is accepted that you can burn fuels that have already been used in light water reactors, and you can burn oxides mixed with uranium, plutonium, or thorium. This means that in the new fuel cycle reactors, you have the advantage of burning fuels that you already have, meaning that you save money because you're not spending it on storage. All these processes are still very complicated and not firmly established. They are thinking very seriously about exactly how to evaluate how much a nuclear power plant really costs. We can burn fossil fuels. There's still plenty out there. When you take a combustible element from a light water reactor, the problem is that you have lots of energy there. The problem isn't that you have residue. The problem is that you have an element that can still produce a lot of energy. So, in that sense, the costs of storage can be transferred in reality to a decrease, because you're never going to spend that on storage. Rather, you're going to take advantage of it and generate more energy. So all of these new fuel cycles are what require more analysis, because they imply, without a doubt, the advent of new technologies. And that's where the most work is being done right now.
Or perhaps the answer lies not in splitting atoms, but in joining them. Instead of fission, fusion. For while fission tends to break things up, fusion brings things together. We spend both time and money to collect the sun's energy, but can we reproduce that energy? Smack dab in the geometric core of our closest star, Some 700,000 kilometers beneath the surface of the Sun, the most powerful source of energy we know operates around the clock and provides our planet with light and heat. The way the Sun actually works was a mystery up until 1938. Albrecht Bethe and Charles Critchfield, both specialists in atomic physics, speculated that stars produced their energy by means of nuclear fusion. That meant hydrogen atoms fusing to produce helium and powerful radiation as a byproduct, the same radiation that bathes Earth in light and heat, the same radiation that illuminates the Milky Way. Astronomers estimate that the Sun's core is subject to pressure approximately 225,000 times greater than that exerted by our atmosphere on the surface of the Earth. On the Sun, temperatures reach 15 million degrees centigrade. The combination of such tremendous heat and pressure is what causes nuclear fusion. Every second, 580 million tons of hydrogen are transformed into helium.
Fusion is the reaction which is the opposite to fission. I think people are familiar with fission. Fission is the reaction where very heavy nuclei are breaking to produce more stable, smaller nuclei, and this is releasing a lot of energy. On the very other end, that is when you bring together very light nuclei, they can fuse, and when they fuse, they produce other nuclei, heavier but more stable, and thereby they release a lot of energy. And this is a reaction which is more or less the basic reaction in the universe in which we are, because it's a reaction you find in the stars, and the stars draw their energy, which compensates the gravity which would bring the stars to collapse. The stars take their energy from fusion reactions, and there is in stars a balance between the fusion energy and the gravity, and this makes us the stars exist, and that we exist also ourselves.
Imitating the process used by stars to produce energy is one of science's oldest dreams. Hydrogen nuclei carry a positive charge, and according to the laws of physics, two positively charged particles won't bond. To overcome such strong electrostatic force, these nuclei must be compressed and heated at temperatures of up to 100 million degrees centigrade. But there's no place on Earth where such conditions exist, and to produce them is no easy feat. Nuclear fusion has been achieved on Earth, but without sufficient control. It was used to produce the H-bomb in 1952. To obtain such extreme temperatures, its designers used nuclear fission. Regardless of the military objectives at stake, this experiment constituted the first key step in achieving fusion. But how could the process be reproduced and controlled? Given the extreme conditions required, fusion calls for fuel to be tightly contained. Hydrogen must be heated to split up its atomic structure. Its electrons and nuclei break up and form a kind of chaotic soup called plasma. Then it must be heated further and compressed so densely that it reaches temperatures of between 100 and 200 million degrees centigrade and the requisite density for more than a second. Under those conditions, nothing can maintain its initial solid structure. Reactions such as this must take place literally in the air. This curious nuclear levitation can be obtained with lasers and also with magnetic fields. In order to produce nuclear fusion, we have designed sophisticated machines, small Earth-based suns that allow us to imitate the star's light and heat-generating processes. The most advanced device up until now is the tokamak, a magnetic confining device developed in the former Soviet Union midway through the 20th century. When European industry took an interest in nuclear fusion, the Joint European Torus Project, better known as JET, was established. The experiments carried out in these devices have shown great promise right from the start. In fact, the appropriate conditions for nuclear fusion have been achieved, but separately. The different efforts have never joined forces. The JET project, for example, managed to fuse hydrogen nuclei, but in a very inefficient way, spending more energy than was produced. The next step is a new machine called ITER. It's being built jointly by the United States, Europe, Russia, and Japan. The ITER is considered the most avant-garde scientific endeavor after the space station.
Right now, we foresee that by the year 2020, mankind will have the technological skill to produce fusion that can generate great amounts of energy at a relatively low cost, or rather with minimal energy input. That's to say that the factor of multiplication of that energy will be such that with only this small amount of fuel, this small amount that we're going to introduce, we'll be able to get from the water, which we are going to heat to 100 million degrees, will produce around 500 million watts of thermal energy that we can then use to produce electrical power.
We want to light up the darkness, to be warm in winter, and to have air conditioning in summer. We want our cars, trains, and airplanes. We want to have our factories working at full capacity. But at the same time, we need to keep our atmosphere free of the negative effects generated in the pursuit of our dreams. Energy is what marks man's growth and the progress of civilization. It's the motor that drives expansion, and it's also the key to environmental equilibrium. Energy is the main factor of inequality between social strata, the problem and the solution. It's the future, for better or worse. The answer may still lie deep in the heart of far-off suns, but little by little, it appears that mankind is steadily closing in on the secrets of the universe.